right, great. All right, good morning. Any questions to get us started with today? Okay. All right, so what I'd like to do is to continue discussing the thermochemistry chapter, which is chapter 5. So in the previous lecture, what we dealt with was this idea of kinetic energy and potential energy. And in chemistry, the potential energy that we're, excuse me, most often concerned with is electrical potential energy, the interactions of charges, of electrical charges. Okay. When it comes to kinetic energy, which is the energy of motion or energy associated with motion, we're most often concerned really with heat. Because in heat, we're really discussing molecular motion, motion of atoms and molecules and ions and such, okay? So let's take a look at an example. Excuse me. Let me bring this up. An example, this is a very standard type of issue, which is called understanding the definitions of heat and work. So let me do the following, which is I'm going to draw a little diagram. There we go. We've got. Okay. This is called a gas cylinder. Okay, it's called a gas cylinder. And essentially, this is the principle behind an internal combustion engine, an automobile engine, which burns fuel with the idea of doing mechanical work. So this outside here is an insulated container. When you insulate something, there's two types of insulation. There's what we call electrical insulation. So if you have a wire, an electrical wire, you often coat on the outside an electrical insulator to keep the electricity contained within the wire. That's an electrical insulation. But there's also thermal insulation. And thermal insulation is where you want the heat or you want the thermal energy to be contained to a particular space. So I'll shade this in to indicate that this is a thermal insulator. Okay. Thermal insulator, what it does is it slows down. It doesn't stop it, but it slows down the transfer of energy, thermal energy, between the environment and this region on the inside, which is what is just a water bath. Just like a little bathtub. Okay, so you have a little bathtub on the inside, you have this insulator here, and that insulator is essentially trying to slow down or stop the transfer, what we call heat transfer, between the environment. And the environment is called the surroundings. Okay, that's the environment around this gas cylinder, okay? And so here's what happens. There's several different possibilities, but one possibility is that something occurs inside this cylinder here. It's just a cylinder. And you'll notice that it has this little bar here, and then it has a little rod right here, okay? So this is called a piston. This whole thing here is called a piston. So there's many parts of this device, right? It's not a simple device. It has a piston, it has a cylinder. This is a thermometer over here. Okay, it's for measuring temperature. You then have water, there's a water bath there, and then there's an insulated container to slow down the transfer of heat. So here's what happens. When you have two objects that are at different temperatures and they're in contact with each other. So what I'm going to do is I'm going to say this is at a temperature. I'll call it T1.
Oh, cool.
And this is at a
Oops, sorry, I forgot the R.
If T1, meaning the temperature over here, is greater than T2, which is the temperature over here on the right side, then energy will flow, I'll put that in quotes, from region 1
dressed in a suit
to region 2. Okay, so if the temperature over here on the left side is greater than the temperature on the right side, energy will flow from that first region, region 1, into region 2. And we call that flow of energy, we call it heat transfer. That's, I guess, the technical name for it. Sometimes people just call it heat transfer. It's heat. The symbol for heat is a Q. Typically lowercase. It can be uppercase, but it's typically a lowercase. Okay. So energy, that's if temperature 1, I'm sorry, if the temperature at region 1 is greater than region 2. If it's the opposite, if the temperature in region 2 is greater than the temperature in region 1, then heat transfer will move from region 2 to region 1. Okay, so if the temperature is greater over here, the opposite will occur. Heat will flow in the opposite direction. Okay, that is often referred to as the Zeroth Law of Thermodynamics. Okay, now what happens if they're the same? Let's say that T2 is the same temperature as T1. If they're the same temperature, we have no heat transfer. There won't be any transfer of heat. So if you think about this, you understand this kind of implicitly from your experiences, right? You touch something that's hot, it feels hot, right? The experience of something feeling hot is that it's transferring thermal energy or transferring heat from the hot object to your object, which is your hand, which is colder. On the other hand, if you touch something that's very, very cold, you feel the heat transfer from your hand into the cold object, and that will feel cold to you. So your senses are kind of attuned to being able to figure hot versus cold, but not perfectly, right? We've all had experiences where something kind of felt hot, but it was actually cold, or vice versa. So it's not perfect, but it is at least a sense of temperature differences. And the way that works is through heat transfer. Okay, so what we're going to look at is heat transfer.
Wait a dang minute. Who said I'm coming during lunch? Lunch is my free time. Oh, but when's the after party?
Yeah. Okay, so what we're going to do is we're going to look at heat transfer from this gas cylinder. So there's a couple ways that could happen. One way would be that there's a chemical reaction inside this cylinder. And that chemical reaction can release thermal energy or transfer heat into the water. So heat might flow out to the water. When that happens, we call that an exothermic process. So exothermic is the case where heat is produced by a reaction. We're talking about chemical reactions. And released to the water. Okay, so it goes into the water. Essentially what happens is the reaction results in the temperature increasing. And so since the temperature is higher inside the cylinder, heat will transfer to the water. Now, what happens when heat is transferred to the water? The thermometer measures that as an increase in temperature. So the temperature will increase if heat is going into the water. Now, it turns out there are chemical reactions in which heat is not released, but heat is actually absorbed by the reaction. The reaction actually absorbs heat. And you maybe have seen these in these gel packs, these cold gel packs where you break a little device on the inside, usually a little piece of metal, and then it crystallizes and turns into a gel. When that happens, it gets cold. You'll experience that as a cold pack, right? So that cold pack, what's happening is it's not exactly a chemical reaction, it's really a physical process, but it's analogous to a chemical reaction. As the reaction occurs, heat is absorbed from the surroundings. So if you touch it, heat goes from your hand into the gel and you experience that as cold. That's called an endothermic process. So endothermic is the opposite of exothermic. So heat is absorbed by the reaction. Now, when that happens, with the thermometer, the heat's being absorbed by the reaction from the water. So the heat's going from the water into the reaction. So the thermometer gets colder. It measures it as a lower temperature. Okay. So let me write that down a little bit. I'm going to put a couple notes here for you, which is that if a process is exothermic, most of the processes we look at are exothermic, but there are some endothermic. Heat is released to the water, to the water bath. And the temperature of the water increases. It goes up, it gets hotter, okay? If it's an endothermic process, heat is absorbed from the water. The reaction is absorbing. And the temperature of the bath, the water bath, right, decreases, goes down. Okay. There's also what we call a Sine Convention. Okay, there's a Sine Convention. The Sine Convention, what we mean by that is a sign agreement. We need to know whether something's positive or negative because heat can go in or out. So remember, the symbol for heat or heat transfer is Q. Okay, so here's our convention. If it's exothermic, Q is negative. I'll put a little circle around it. It's negative, okay? If it's endothermic, then Q is positive, okay? What we're going to look at is actually measuring values. We're going to look at numbers, amounts of heat that's transferred in a reaction. So we need to know whether it's going to be positive or negative. So that's heat. Heat is, we're going to talk more about heat when we get to calorimetry, but that is one way in which energy can be transferred from the reaction into the water, or from the water into the reaction, into the gas cylinder. Okay, so that's heat, and there's our convention. And you want to memorize that. You just want to remember that if it's exothermic, that's negative. If it's endothermic, that's positive. Okay. Now, there's a second form of energy, which is called work. And the symbol for work is W. So we talked about heat, which is Q. Now we're going to talk about work. So we talked a little bit about it yesterday in the previous lecture, but work is essentially when you move an object mechanically. So if something has a mass and you push it, for example, you're applying a force, right? If that mass moves some distance, I'll write D for distance, okay? So now the mass is over here. If you apply a force and the mass moves, you've essentially used energy to move it. And that energy is called work. Okay, so that's mechanical work. Now, in theory, if there's no friction, there's no, you don't really have to apply much of a force, so there wouldn't be much work done. But there is friction on a surface, so with that friction, you have to apply a force and overcome that friction. So there's work done. Okay, so that's one form of mechanical work. What we're going to look at now is a slightly different form of mechanical work, and that has to do with the cylinder, the gas cylinder. So when you notice sort of the picture, you'll see a couple of details that might, you may not even notice it actually, unless you really look. So let's remind ourselves, this is the cylinder, just like a cylinder, right? Like a graduated cylinder in a chemistry lab, or, a coffee cup is a cylinder, right? A coffee cup is the shape of a cylinder. So we have this cylinder. We're not talking at all about what's really going on in there. That's kind of mysterious at this stage, but we'll get into it when we talk about calorimetry. But all we're going to claim is that there's some sort of gas in there. There could be more than one. So there could be a mixture of gases in there. So imagine you've got oxygen or air or water vapor, some kind of liquid, some sort of gas in there, okay? And then we have this piston. And notice there's like this vertical arm here. And then we've got a little horizontal piece right there. Now remember, this is three-dimensional. It's really a cylinder, right? So it really looks like that. So this little thing here is really a circle. It's really a circle. So this is a little more accurate view of what it looks like. Okay. So if you've ever seen an automobile, like if you're really into cars and you are interested in the engines, you will sometimes see numbers given. So the number might be 1.6. And they even put a little plate on the car on the side usually when they do that. Or it might say 2.0. Okay. That number is referring to the volume of the cylinders, these gas cylinders that are in the engine block. Okay. So typically a car has either 4 or 6 cylinders, or maybe 8 cylinders, or even 12, I guess, if you have a, I forget the British car, that British car that people like to have is 12 cylinder. So let's say you have 4 cylinders. If you have 4 cylinders and it's 1.6, you divide it by 4. So each one would be 1.6 divided by 4, which is 0.4, okay? Well, that number is liters. It's the size of this cylinder that we're talking about over here, okay? So if you had 4-cylinder and it was 1.6 liter, that would mean that each one is a fourth of 1.6. So that would be 400 milliliters, 0.4 liters. Okay. So that's really where that number is coming from. So the idea is the following. If you have a gas, you've pumped up a bicycle tire probably at some stage, you realize that it takes work, it takes energy to pump up a tire, right? You have to push down on it. And the reason it takes work, the reason it takes energy to do that is you're having to pump in, you're having to push in a gas, but there's already gas in there. And that gas is pushing against the air, the gas that you're trying to put in there, the air that you're trying to put in there. They're pushing against each other. So you have to overcome the force of the air that's already in there to push more in there. So that's why and as you continue going, it gets harder and harder and harder because there's more and more gas pushing against you. So that's sort of the principle that we're talking about here, which is that if we're going to push against that gas and push it down to a smaller volume, that takes energy. It takes, it takes energy to compress a gas. So compression of a gas, let me just write it, it's compressing a gas, requires energy. And that energy, we call it work. And the symbol for work is W, okay? So if you want to push that gas down to a smaller volume, that's going to take energy in the form of work. So in a way, here's what's happening. When you compress a gas, you're actually giving it energy. You're actually adding energy to it. It actually has more energy at the end than it did at the beginning because you put the energy in to compress it. So where'd that energy go? It goes into the gas. It doesn't disappear. It's not gone, it's there. So compressing a gas is adding energy to it. And so we have a sign convention for that. If you're adding energy to something, the change in energy is positive. So our sign convention, we had our sign convention for heat. We have a sign convention for work. If you compress a gas, now how do you know you compressed it? The volume got smaller, right? If it got smaller, that's compression. So if you push down on the gas and it has a smaller volume, you've done, the terminology is you've done work on the gas. Actually, one of the most difficult things for people is the terminology here. Once you get the terminology down, it's easy. So if you compress a gas, we would say that you've done work on the gas. W is positive, okay? Now, what about the opposite? What about expansion of a gas? Okay, expansion of the gas means that the volume got larger. So essentially what happens now is the gas expands. It's now all the way up here. So now the gas occupies a much larger volume. So if the volume gets bigger, that means it expanded. Okay. Well, essentially what happens here is the gas is pushing against the air. So often you'll see it says 1 atmosphere. 1 atmosphere is just telling you that there's air pressure outside. So to push the air out, it takes energy to push the air away. So it's the opposite. So if a gas expands, then your work is negative. And the way we would say, the way we might phrase that, again, the terminology, be careful with it. The way we might express that is to say that the gas did work. Okay, the gas did work. There's other ways to explain, to put it into words as well, and you will see that when you do problems. But essentially what happens is when a gas expands, it loses energy. The gas loses energy, and the energy goes out to moving this mass, removing this essentially. So if the cylinder is compressed, work is positive. If the cylinder expands, if the gas expands, then work is negative. Okay? So 2 sign conventions. Now what I'm going to do is I'm going to put it together. What I'm going to do is I'm going to claim that there's something called delta E. I'm sorry, let me put a U. Delta U is equal to Q plus W. And remember, this is our heat transfer. And this is our work. Okay? This is called the change in internal energy. And it refers to the gas in the cylinder. Okay? When we talk about internal energy, we're talking about the gas in the cylinder. Okay? We're not talking about the water. We're not talking about the thermometer. We're talking about the gas that's in the cylinder. So the idea here is the following. This gas has a certain amount of energy. The molecules are bouncing around. They're at some temperature. There's energy in there. It's difficult to figure out how much energy it has, but what you can do is you can say the following. If you add energy in the form of heat, if you're putting in some of this heat, the energy will go up. It'll have more energy after you put the heat in than it had before. So there's a change in how much energy it has. So the change in internal energy, delta U, is equal to the final amount of internal energy it has minus the initial. So let's say it has 50 units of energy, but then you put some heat in, another 10 units. Now it would have 50 plus 10, it would have 60 units. So the change would be 10 units. That's how much it went up by. So this is how much it goes up by or it goes down by. And what's important about this is that it's very simple. This might go up by 10 because we put in 10 units of heat. Or it might go down by 10 because we lost 10 units of work. So it's only these two simple terms that tell us how much the energy changes by. So that delta U ends up being pretty important. So it's sometimes referred to as internal energy. Sometimes it's referred to as just energy. I think sometimes the ALEKS problems, they just call it energy. So if they call it energy, the energy of the gas or the internal energy of the gas, they're talking about this right here. Okay? So a lot of background there. So what I'm going to do now is I want to come back and show you a problem because there's a lot of background in that one. Okay. Okay, so we got our gas cylinder. There's a mixture in there. Dun, 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 dun. Okay, so let me just put in there. It says, after all the intro, that 139 kilojoules of heat flows into the system. During a reaction. The position of sorry, kind of tongue-tied today. The position of the piston is monitored. And it's determined, very long word problem, that the system does 155 kilojoules of work on the piston. Okay, So I left out the first full paragraph because it just describes the picture. Again, the idea here is you've got this whole device here. There's your thermometer. And then you've got your gas cylinder with the piston. There's the gas. And then you got your water here, right? Okay. And then they ask you several questions. Okay. So there's 4 questions that are going to be asked here. So the first question is the reaction exothermic or endothermic? Okay. So let's answer that question first. Okay. And then we'll come back and we'll look at the others because I think it's useful to kind of analyze what's going on. The way you determine whether something is exothermic or endothermic is you look at the heat flow. Don't worry about the work. The work is associated with the internal energy, the total energy, all of that. That's important. But in terms of endo versus exo, the heat is the only thing that matters. Did heat flow in or out? And again, remind yourself, you understand what that means, right? If you draw a bathtub and you fill it up with hot water and you get in that bathtub, you realize that heat is being transferred from that hot water into your cold body and it warms you up, right? That's heat transfer, okay? We haven't talked about the molecular level of how it works, but you have a macroscopic view of how that works. So all we have to do is look at this. And we just have to be sure we know what the system is. I mean, what the terminology is. So when they see how they use this word system, the system is the gas, which is the reaction. The reaction is occurring in the gas. So it's right here. Okay. So again, if heat leaves the gas, that's exothermic. If it goes into the water is what I mean. So if it leaves the gas and goes into the water, that's exothermic. Okay. If heat goes into the gas, that's endothermic. Now you might be confused. You might say, well, wait a minute, you said go out, you said almost the opposite, because I was talking about the water, right? If heat goes into the water, that's exothermic. But that's because it left the gas, right? If heat goes out of the water and into the gas, that's endothermic, okay? So the word system here, be careful, the word system means the gas in the cylinder, okay? So if they say that heat flows into the gas or into the system, then Q is positive and that's an endothermic process, okay? So heat flowed into the gas, which is the system. So that's endothermic. And they don't ask you to do the sign here, but I'm going to put it here because we'll need it for another question. So here's how you apply the Sine convention. If it's endothermic, that's positive. If it's exothermic, it's negative. So we put, and I recommend just go ahead and put a plus sign, 139 kilojoules. Okay, so had it said that heat flowed out of the system, that would mean out of the gas and into the water, that would be exothermic. Okay, so we generally, if you're an engineering major, it'll be the opposite, but you'll worry about that when you take an advanced thermodynamics course. But for a chemistry class, the way you look at it is the gas is the system. And so if heat flows into the system, it's positive. If it flows out of the system, the gas, then it's negative. Okay. Second part of the question. I hope. Oh, shoot. I'm sorry, we have a little computer crash here. I'm gonna have to restart it. Just take a minute. 5. Okay, second part. Does the temperature of the bath go up or down? Okay, so that's the second question. And you have 3 choices. It could either go up, it could go down, or it's neither. Okay, so that's completely connected to heat. All you got to do is look at heat again. Temperature and heat are intimately connected. Okay, so here's the idea. What we just determined is that heat flowed out of the water, right? It went into the gas. So that means you're losing heat, you're losing energy in the water. So what'll happen is, as you lose energy in the water, the temperature will go down. Okay, the thermometer is put in the water. It's not put in the gas. If you measure the temperature of the gas, it would be different. But since the thermometer is placed in the water, you have to look at what happens to the water. So if the heat went from the water, the temperature of the water will go down. Okay, so our answer here would be that the temperature of the water would go down, it would decrease. And the reason for that is that the heat flowed from the water. It'd be like a cold bath, right? Think about it this way. If you had cold water, if you had hot water, and then you jumped into the bath, the hot water would transfer heat into you, so the temperature of the water would go down. Okay, so as the water loses heat, its temperature goes down. Okay, let's look at the third part. The third part, there's 5 parts to this question. Does the piston move in or out? Now let's be careful about the terminology here. In or out, okay? What they mean is, does it go up or down? Now, the reason they don't say up or down is because if you turn the thing upside down, what used to be up is now down, and what used to be down is now up. So they don't want to say up or down. They just want to say in or out. So in means smaller volume. Out means bigger volume. Okay. So in is larger volume. Out is, I have it the opposite way. I don't know why I got that wrong. So in is smaller volume. Out is larger volume. Okay, so let me show you what I mean by that. If you have the piston like this, and then it goes like this, this would be moving out, right? And then if it looked like this at the end, then this would be moving in. Okay, so moving in means the volume's getting smaller. Okay, now here's how you figure that out. That has to do with work. So I'm going to underline that second part right there. Work on the piston. So work on the piston. So what they're saying is the gas, remember the gas is the system. The gas is doing work on the piston. Okay. So what that's meaning is energy is going from the gas to the piston. So it's pushing the piston out. So if they say that the gas or the system or the reaction does work on the piston, what they're meaning is it's going out. Okay. So for this one, our answer would be out. If it says that the piston does work on the system, or the piston does work on the gas, or the piston does work on the reaction, then that would mean in. Okay, so again, think about it like a bicycle tire. You're doing work on the gas. If the gas pushes your hand back out, then the gas is doing work on you. It's pushing you. Okay, so this would be out. All right, so let's move on to the fourth part. The fourth part is, does the reaction absorb or release energy? Okay. So this is the fourth part. Does the reaction absorb or release energy? And here's how you tell that. That's when you use this equation. Okay, delta U equals Q plus W. If delta U is negative, then the reaction releases energy. Okay, negative meaning you lost. So think about it in terms of money. Energy and money are kind of analogous in a way in terms of how they work. They're both what we call scalar quantities. So if money comes in and money goes out and you have less money at the end than you had at the beginning, that's negative. If you have more money at the end than you have at the beginning, that's positive. Same is true for energy. If you have more energy at the end, that's positive. If you have less energy, that's negative. Absorbing energy is positive, releasing energy is negative, right? Again, it's very analogous to how money works numerically, okay? So all you got to do then is you just got to add the two numbers together. We already figured them out in our previous one here. We already figured out that Q is positive 139. Now, we didn't figure out what the value of, what the sign of the work was. So let me show you how that works. The sign of the work is this. If the system does work on the piston, it's negative because the system is giving the energy to the piston, okay? So since it says the system does the work, our sign there would be negative, okay? Let me come back over here. All right, so let me put it here. If system does work, and again, they're using the language very interchangeably. System, reaction, gases, right? All three of those things are referring to the same thing, okay? So if the system does work, W is negative, okay? If the piston does work, W is positive, okay? So let's put it together. Q was positive 139 kilojoules. And now W, since in this problem, the work was done by the system, the work is negative 155 kilojoules. Okay, so we've got a number there. So now all we got to do is add those together, right? So the arithmetic is ridiculously simple. You just got to add two numbers together, but you got to get the signs right, right? If you get the sign of one of them wrong, you get the wrong answer. So delta U. So our answer is, well, we have to calculate it. So if you take 139 and negative 155, you get negative 16. Okay, and then we come back over here. What we do is we say the following. If delta U is negative, then the reaction releases energy. Okay, that would be our answer. Now, I just want to kind of just briefly kind of explain what happened. What essentially occurred was, again, here's our system. This is the gas. some energy went in the form of heat. But then the system did this, right? It released energy in the form of work. So again, think about it kind of like money, right? If someone gives you $139, but you give someone else $155, you've lost $16. That's your net change, right? That's essentially what's happening here. So you just need to determine what the sign of each of those two values are. If this was positive 159, that means you took in more heat than you lost in the form of work. So you would be a net change that's positive. Wouldn't be very big, but it would be some positive change, okay? So it's really the only thing that's really difficult about this problem, and there's 5 parts there, right? So there's a lot of little mistakes you can make, is that you just got to get the terminology down. And they do play around with the terminology, and that can cause problems. So just think of it like this. Your system, you got heat coming in or out. You got work coming in or going out, right? So you got your piston here, and then you got your water bath here. So heat, if it goes from the water into the system, Q is positive. If heat goes from the system into the water, Q is negative. In terms of the work, if the piston does work on the system, W is positive. If the system does work on the piston, W is negative. And then you just add those two together. Exothermic is if Q is negative, endothermic is if Q is positive, and you'll be set. Okay. Now, I don't really have enough time to kind of go over a whole different type of problem. So let me do this. I'm just going to show you one more example. So same setup, right? So we got our same little diagram here. The diagrams on this are not going to change. Okay, so there's your water bath, there's your thermometer. Okay, that's how you're measuring the temperature there. Okay, so in this particular one, again, there's a whole intro describing the picture. And what they do is they say the reaction absorbs 185 kilojoules of heat. Energy. Be careful. So it absorbs energy. Okay. Next thing it says, position of the piston is monitored, and it says the piston does 364 kilojoules of work on the system. Okay, so read these very careful. So first question, is it endothermic or exothermic? Okay, second question, does the temperature of the water go up or down? Third question, piston moves in or out? Fourth question is heat flows into or out of gas mixture? And the last question is how much heat? Okay, so again, same questions, it's just a little slightly different modified situation. So be very careful about this one. What they did is they did not say heat, they said energy. This is not heat. Energy is the delta U. So what they're telling you is delta U is absorbed, that means positive 185. If they had said that it absorbed 185 kilojoules of heat, then Q would be positive 185. But it says energy is delta U, okay? Now remember, delta U is Q plus W, right? So they didn't tell us the heat. They told us the energy. They also say the piston does work on the system. Okay, that's the opposite of the previous example. Now the system is getting the energy. So W is positive 364. Okay, why? Because the piston did work on the system, meaning the energy is going from the piston into the system. When you do these calculations, you're really concerned about the system, which is the reaction of the gases. So now we know W is 364. So delta U is equal to Q plus W. Suppose we wanted to know what Q is. We would just subtract W from both sides. Okay. We can only tell if something is endothermic or exothermic if we know Q. If Q is positive, that's endothermic. If Q is negative, that's exothermic. So we got to calculate Q. So we take our delta U. Our delta U is 185. And we subtract our W, which is 364. And that's going to give us Q. Okay. So 185 minus 364. Let's see, what is that? 185 minus 364. I guess I could do that. I can do that, right? 364 minus 185. 971. So negative 179 kilojoules. That's Q. So now we've got a couple of answers here. We do know how much heat flows, minus 179 kilojoules. We just calculated that here. We also know whether it's endothermic or exothermic. Remember the convention, exothermic negative, endothermic positive. Endo means into. So if something comes into, that's positive. If something goes out, that's negative. Okay. So it's negative, so it's exothermic. Okay. Now, let's get to the temperature of the water. If it's exothermic, that means heat's going from the gases into the water. So that's heat flow. So if heat goes into the water, the temperature of the water is going to go up. So our answer there would be up. Okay. Does the piston flow into, or I'm sorry, does the piston flow in or out? Well, in or out depends on what W is. So the piston in and out is work, it's W. So we have to figure out what happened to W. The piston did work on the system. So notice the wording switch here. The wording in the previous one was the system did work on the piston. Now they're saying the piston did work on the system. Okay, so if the piston did work on the system, that means energy went into the system and away from the piston. So energy going into the gas mixture, which is the system, that's compression. Compression is when you do work on the system. Expansion is when the system does work on the piston. Okay, so it's going to come in. We're going to be doing work. The gas will have more energy in the form of work, this transfer of energy from work at the end than it had at the beginning. And then number 4 says, does heat flow into or out of the gas mixture? Well, that's pretty simple. We already figured out that it's exothermic. So that means that the energy, the heat, remember, not energy, but heat, is flowing from the gases into the water. The water got hotter, right? So that means that it flowed out of the gas mixture. Okay. So what I would recommend is have a little sheet next to you that has the Sine Convention and also the language convention, right? So sort of like, you know, you could do this on even on a 3x5 card. You have heat and you have work. And so if it's exo, that's negative, and heat flows into the water. And then if it's work, what you could do is you could say it's positive if you have work done on the system, right? And then you can have the opposite, right? You can say heat is endothermic, which is positive if it comes from the water. And then you could say work is negative if it's done by the system. And then delta U, you can just calculate that from those two, okay? So if you have that next to you, so you can just kind of, when you do these problems, remind yourselves of that convention, you should be pretty well set, okay? So that was a lot. That was a lot for one type of problem, but that problem is so involved that it gives people a lot of difficulties. So I wanted to spend some time on that one. And again, the significance of this, just to remind you, the significance of this is that when we run chemical reactions, we generally run them for a reason. And one of the reasons we run chemical reactions is to transfer energy. So when we boil water to generate energy to run power plants, so for example, a nuclear power plant operates by boiling water. A coal-fired or oil-fired or gas-fired energy factory is essentially boiling water. So heat transfer is all about the boiling of the water, and then we can use that to generate electrical energy or mechanical energy, okay? So a lot of it starts with essentially chemical reactions, okay? So what we'll do tomorrow is we'll look at a slightly modified problem where we're going to look at enthalpy. And then if we have time, we will look at calorimetry, which is section 5.4. But calorimetry is a pretty involved section, so we'll probably only look at a little bit of it, okay? So good luck today. Good luck with everything, and have a great day.
Thank you, Professor.
Thank you.
Au revoir.